here. Alrighty, so let's talk about amides. We have some interesting things to talk about with amides. Of course, amides follow the general pattern of having a carbonyl and an amine together. What are you doing? When we're talking about amides, something important to note is we have a pretty significant resonance contributor to the amide. One that's more significant than we might see in other ones. Wow, and it's do exactly the same thing. Okay, there we go. This is actually a pretty significant contributor. Significant. If we compare this with something like an acid chloride, if we try and resonate that thing, if we resonate the acid chloride, you have a positive chlorine, negative oxygen. That's not as good, right? Obviously, we don't normally see very many positive chlorines. Chlorine is actually, chlorine and nitrogen are roughly the same electronegativity, but nitrogen is just better at kind of handling the positive charge a little bit better. We don't really see this as an important player in the amide, or I'm sorry, in the acid chloride, where we do see it as being important with the amide. And the reason that we're looking at this is because as a result of this resonance, because the amide is more, I'm going to draw them both as single bonds here. To see that amides have a pretty planar character. That we're not really going to see with the acid chlorides. And it's really important because we're going to see that stereochemically it's actually pretty tough to switch positions on an amide. So if you have an amide that's got one other substituent on it, if you were to try and rotate these around, we don't really see that happening as much. We don't really see this happening. This is about 90 or so kilojoules per mole. That's a pretty big energy gap. That's a fourth of a CH bond, right? So these don't tend to rotate as much. So we just have some interesting, important aspects when we come to proteins. When we talk about amino acids, they are all connected by amide bonds. Yeah, Ani, of course. Let me just finish this thought, and then we'll deal with that. So it's tough to rotate, and this will become super important for proteins, which use amide linkages. All right. Okay. Let me hop over for a sec. So, Ani, you had messaged me. Can you just type it out in general real quick? Just so I don't have to switch over to the private one, since I have the screen recorder going. I saw it kind of pop up for a second. I think she had wanted to talk about the exam. I think we'll make it the 15th. So, I don't know which day it was set for, but we'll make it the 15th. Okay, so we'll just write that randomly here. Wrong month, huh? 11/15. There we go. So it'll be, I I believe that's the Monday, right? Go ahead.
Quick question. What was
Oh, CF is like EG or IE. It's Latin. I don't remember, but it means compare it to or compare it with. Um, like EG means for example, and I don't have any clue what it stands for. Uh, yeah, I will write this. Compare. So it's yeah, it's just means compare it with something else. So we see that we can't rotate these very easily, but we can rotate acid chlorides. All right, so it will be on amines rather, carbacids and derivatives. So there are the SIs. Mrs. O's SIs are in the extra resources tab, as well as the keys, and they actually line up for once, so that's good news. So I would suggest you take some time going over those because we'll have good practice material. And so, yeah, cool. Okay, let's talk about amides then. So amides we can make from really any of the other functional groups. We can take an acid chloride, and we'll make our amide. Remember, we do need two equivalents there. So just keep that in mind. Typically, we can only do this with primary or secondary amines or ammonia. We don't really see this happening with tertiary amines because we're going to end up with something positively charged there. So a little bit less stable. So usually you'll see either a primary, secondary, or ammonia amine there. So those are going to be our kind of common ones. And that's kind of the best way to do it. You can do them with anhydrides, exactly the same thing, although we will really only need one equivalent of our amine. Esters and acids are a little bit harder to get to amines, but if you really cook them, if you really cook them with acid and everything, you can get them to form amines. So esters and acids, and really you can really get them to go if you really cook them for a long time. So easier to just throw the chlorine on, make them into an acid chloride, and then go ahead and do your ammonia or whatever amine you're using. So not really the easiest way to go about it. And conversely, it's actually pretty difficult to get an amine off because they are the least reactive of all of our derivatives. So you can hydrolyze them. We'll just use plain old amide here. Let's look at hydrolysis. Hydrolysis is going to follow the same pathway as many of the previous things we've done. Use acid and water and some heat, and you can hydrolyze it back to your carboxylic acid. Tough reaction to do, though. It's not very fast. It's not very effective. But we can do it. The mechanism is going to look much the same as hydrolysis of esters. So first step, because we're doing it in acidic conditions, we'll have our acid here. Oops, wrong color arrows, but whatever. All these will be equilibrium steps. We'll have a water molecule attack. Pops it open. And if you will allow me, I'm going to do it in just one step. I'm going to just proton shift this, and I'm just going to move our proton to the other one. Technically, the steps are you would take the proton off, have a water molecule come, remove the proton off the OH2, and then another step, the NH2 grabs a proton from the H3O+. But I'm going to just go ahead and write it out. Now we have our NH3+, and then we're going to go ahead and close down. Remember, a proton shift is really several steps, but I'm cheating in the interest of efficiency. So exactly like the ester hydrolysis. And poof, there we have it. You'd probably end up with NH4 plus as your byproduct. It's probably going to actually be, it's better of a base than the water is. So let's go ahead and actually use that. NH4 plus NH3. Let's get that arrow then. Because you're in acidic conditions, you're going to end up with the ammonium salt at the end. Doesn't really have a huge impact because we're more interested in our carboxylic acid at this point, but that's how we do it. We can do it with basic conditions. Looks again exactly the same as ester saponification. So base hydrolysis. H comes in. And then we're going to have the thing close down, kick out our ammonia. We make a nice strong base, the amide ion, which is going to go ahead and grab a proton off something like our dear friend water. Amide's a much stronger base than water is, so we're going to go ahead and that makes it essentially just an H3 and OH minus. Those are your other side products for this. So base hydrolysis is pretty much exactly the same as for esters, except we have the NH3 coming out. Hooray! Exciting. We can also reduce esters, or amides, reduction. And hopefully we remember this because we just did it. They spent so much time talking about this. Throw it with your LiH4 and water, second step water. You'll end up reducing to the primary amine, or whatever amine you happen to have. So we kind of just completely get rid of our carbonyl this time. That's the interesting part of this. Previously with other reductions, we ended up with OH, right? When we tried to reduce an ester or an acid chloride with hydride, we ended up with a primary alcohol. In this case, it just gets rid of your carbonyl. So we reduce them to plain old amines. All right, so that's our amide part here. One more thing to note, by the way. Amides are non-basic because their lone pair is resonating into the carbonyl, right? So amides are typically non-basic and in fact even mildly acidic. They have pKa's of around 15 or so. make this one about blue. pKa is about 15. Compared with something like ammonia, that pKa is 35. So because of the resonance, they're non-basic, so that lone pair is contributing to the resonance, so it's not going to be used as a base, the lone pair right here. Not really going to be used as a base, and in fact, it's going to be actually a little bit acidic. So, fun fact there for you. So just keep that in mind. So amides are completely non-basic because they are resonating away, right? If we take a look at that resonance form we did earlier, here it is. We have a positive charge on the nitrogen, right? So it's not going to be acting as a base, right? And that negative charge on the oxygen is resonance stabilized as well. So we tend to see these not really acting as bases, as we might see some of our other amines acting as bases. Alrighty, nitriles.
Sorry.
Yeah. Yeah. Where do you want me to go? Just right above. Cool. Okay. Yeah. That means I get a second to drink coffee. Hooray. Cool. All right, let's talk about nitriles. So nitriles, we've seen ways to make them. Mostly that's through SN2 type processes. Use NaCN, KCN, some sort of cyanide source. Through an SN2 reaction, you can get a nitrile. We also saw that with aldehydes and ketones. Like H, why not? We can get a nitrile and an alcohol. So we have a couple of ways to make them. Interestingly enough, amides, if we take an amide and treat it with thionyl chloride, we will get a nitrile. So RCN. Interestingly, isn't it? So we're using similar reagents, we end up getting the nitrile. So it's actually pretty cool. So that's ways we can make them. One, a new reaction. The new reaction being the thionyl chloride. You throw that in with your amide, and you'll end up getting a nitrile out. Nitriles are a bit more reactive than amides are. And so we're going to take a look at a couple of different reactions that nitriles will undergo. Let's take a look at the mechanism for this dehydration of the amide to form the nitrile. Let's look at the mechanism for this. So just like before, because of that resonance, we have kind of this delocalized negative charge hanging around in the amide structure. And let me draw my thionyl chloride. We're going to resonate this and go ahead and attack. So we're going to go ahead and couple this just like before to the thionyl chloride. We'll now have our double bond to the amine part there. We'll have some sort of handy dandy base come along. Maybe it might be a chloride. Gonna come around. add that. Oh, I have no space. Oh, I forgot to close this down first. Hold up. I have to show you where we're generating that chloride from. Hold on. We'll get this part out in just a sec. We have to close this guy down to make our chloride, which then can come in and act as the base here. Oh, there we go. Now our chloride comes in. I'm going to use the better color, sorry. I realize that these can get very clunky structures otherwise. And I better fix these arrows too. Alright, so we will have deprotonated this. So just like before, we have a great leaving group and our imine here. We're going to have another base come along. Perhaps that's an additional chlorine. This one will come from when we kick out the next one. So we have this stuff floating around in there. Sorry. Okay, and then we're going to go ahead and close this down and kick out the chlorine. So just like before, just like with the thionyl chloride for turning the acid into the acid chloride, we are going to end up producing SO2 gas. That's the driving force behind this reaction. It's the reason it works so well. And so as a result, we have our nitrile. We also produce HCl and SO2. This one here is a gas, remember. This is the driving force. Whenever you make a gas in an organic reaction, that's going to force your reaction to drive towards the products by Le Chatelier's principle. The SO2 floats away. All equilibrium reactions, remember, if you take away a product, you end up making more products to fix the equilibrium. So that's our main driving force here. So we're going to end up making 2 HCl's out of this and the SO2. All right, and the SO2 goes and floats away and it goes and does its own thing. All right, this is called, I know, Audrey, you're going to ask what's the name. Dehydration of amides. That's what we'll say. All right, so we end up with the chloride there, and it's going to go ahead and pick off the last little bit there, kick out the sulfur dioxide, which is going to also kick out the other chlorine. All right, and let me just show the whole thing. Yeah, what's up?
Okay.
I figured. I am predicting all your questions. Okay, so yeah, I'll give you a sec to take a look here. So amide treated with thionyl chloride produces a nitrile, and we have a few sips here, and then I'll talk about the mechanism. So first step is we just kind of resonate to have the oxygen be the more negative one, because that's going to be more nucleophilic. So it's going to go ahead and attack our thionyl chloride. Thionyl chloride closes back down, kicks out a chloride. And then our chloride comes in and grabs a proton. And then chloride comes in and grabs a second proton. When it does so, you end up kicking out your leaving group, which is the OSOCl. And by kicking it out, you're producing SO2 gas. So, we might think chlorine's not really a very good base, and this imine thing is not really a very good acid either. So why is this reaction taking place? It's because it makes SO2. So as soon as it happens, the SO2 is gone, it's irreversible. So technically speaking, all these little bits here are reversible steps. except for the last one. The last one is irreversible because once you make SO2, it has bubbled away. It is now in the atmosphere, creating acid rain to destroy the oceans. So it is no longer part of our reaction. So it's just going to go do other nasty things. All right, so that's what we're looking at here. Okay? Yeah, go ahead. Yeah. So recall that if we have, I don't know, x plus y, any sort of equilibrium reaction is all this stuff, right? And if you end up taking away, an equilibrium constant is always constant at a given temperature, right? So this number Kc is a fixed value. And so if we are taking away W, if we remove that, if we take W away, if we remove W, mathematically, because Kc has to be the same number, we end up taking some more X and Y and turning them into W. If that makes sense, right? If we think back to Le Chatelier's principle, if we are removing one of our products, the equilibrium becomes disturbed, and in order to keep Kc the same number, if we remove W, Kc becomes smaller, right? Or rather, Q would become smaller. If you remember equilibrium quotients. But your Q becomes smaller, and then in order to fix itself to get back to Kc, you need to make your denominator smaller, right? To then make the numerator bigger in order to fix this. And so as a result, if you remove a product from your reaction, you force more product to be made. Is this kind of ringing a bell? Okay. To be made. So it's all about the balancing act of Le Chatelier's principle. Again, something you thought you learned in 102, maybe, and have completely forgotten, but it's still hanging around there. So with any sort of equilibrium thing, if you add extra reactant, you make more products. If you take away reactant, you make more reactants. Right? That's how equilibrium works. So it works the same for products too. The more product you make, the less likely you're to make more product. But if you take a product away, or a product goes away as a gas, since these reactions are taking place in solution, if you have a gas leaving your reaction system, that's a product that's removed. So as a result, the Chatelier's principle says we're going to make more products. All right, so that's our driving force here. All right, anytime you make a gas. There's also entropic reasons. If you remember your delta G stuff also, making a gas makes this thing more positive. So your delta S becomes more positive, thereby making your delta G more likely to be negative, more likely to be a spontaneous reaction. So if you thought you were done with thermodynamics and the fun times you had with Gellert or Gaugic, no, not done with those, unfortunately. So that's the reason for this. All right, anyways, now that we've spent some time on 102 material, we'll keep on going. Let's look at some of the things nitriles do. First one we'll look at is hydrolysis. If we hydrolyze, actually technically we just need water kind of in this first step, but let me consolidate here. We usually use acid as the second step. Because step one technically gets us amide, and then we'll reduce it later. So I'm going to actually split this up here as well, just so I can show you the intermediate. So you make an amide first, and then if you go ahead and use acid and heat, you can get your carboxylic acid out. So if you just kind of throw a bunch of acid at this, and again, acid will help this one too, so it just, it just keeps on happening. It's hard to kind of isolate the amide part there, but because the hydrolysis is super slow, this one's really slow, you may be able to isolate your amide. So depends how long you cook it for, right? If you cook it for a relatively short time, you might end up with the amide as your major product. If you keep letting it cook in the acid, aqueous acid, you'll end up making your carboxylic acid out. So this would be hydrolysis. Hydrolysis. Let's take a look at the mechanism. So first step here, we're going to see this is somewhat similar to, let's just do it. Okay, here we go. We'll use our acid-catalyzed version. We'll see we can do it with bases too, just like everything else this chapter, it seems. We're going to go ahead and protonate our amine, or rather our nitrogen. Which is going to make this carbon more nucleophilic. Here's our dear friend, the water. However, doesn't it seem like all these hydrolysis mechanisms are exactly the same? Protonate something, water attacks. All the fun, good stuff. They are the same, right? They're all the same. Alright, so we now have attacked this, going from an sp carbon to an sp2 carbon now. We're going to deprotonate. Oh, shame on me, I'm using the wrong color again. So we've made our acid back. Now we're going to have some fun little resonance happening. Actually, because we're doing acid catalyzed, we can't resonate quite yet. We're going to have to use this as a base first. Remember, these are called Schiff bases. This is really, again, our this is a proton transfer and putting out all the steps. But we're just moving a proton from the OH part to the NH part. Just remember that because this is an acid-catalyzed mechanism, we're not going to see negatives anywhere, ideally. So that's why we're going to protonate this thing first. All right, now we're going to go ahead and close this down. And then last step, we'll just have a deprotonation. So deprotonates, giving us the amide that we're looking for. And look, it's exactly the kind of opposite of the hydrolysis, or making amides. I don't even know what I'm saying. Same exact mechanisms, right? Let me flip this over so we can see the whole thing. So with the hydrolysis, first step protonation, as always in acidic conditions. First step is always protonation. We're then going to have nucleophilic attack, deprotonation, protonation, resonance, deprotonation, and we're done. So it's, I guess I need to have a different arrow for this, don't I? This should be a resonance arrow. But not really worried about that distinction too much. So mechanism, again, pretty similar to what we've seen before. And then once we have the amide, you can see the hydrolysis of the amides. We've just done that earlier, so you can see how that happens as well. So it would protonate again and then go forward and have its fun stuff. So if you just keep going with that, if there's more acid and heat present, you'll end up hydrolyzing down to the OH. Alrighty. Questions on that one? Again, pretty similar to what we've seen before. Alrighty. We can do it with bases too. Let's look at the base catalyzed one. So this one that we just did was acid catalyzed. We can also do base catalyzed. This one, I mean, technically we can leave the first one in the same pot. Just leave it with the H plus and water in the heat and let it go all the way to the carboxylic acid. This one we are going to need to do separate washes with this, with the base one. I'm sorry, we're on Nitriles. And we'll end up getting our carboxylic acid out. So the point of learning both mechanisms, by the way, and both like conditions is sometimes you'll have things that are sensitive to acid or sensitive to base in your reactions. For example, we know that say you had a ketal, you are protecting a ketone for some reason. Ketals are base stable but acid sensitive. So if you wanted to reduce or hydrolyze a nitrile in the presence of a ketal or an acetal, you would need to use the base one. Just like with removing the carbonyl, we had the acid Clemenson reduction, we had the base Wolff-Kishner reduction. So we have different tools for getting the same thing done, just depending on if you have sensitive bits in the rest of your molecule. So let's take a look at what this one looks like, and guess what? It's going to be very much similar to what we've seen before. So OH comes in, nucleophilically attacks the carbon. I guess I'm starting up here. And I'm going to go ahead and draw this. We have our imide. Notice base catalyzed, we have negative charges. That's the happy state. We do not have positive charges when we have base catalyzed ones. Great, so we have now this happening. Another hydroxide comes in, We're going to go ahead and condense this down. All right, technically it might go to the oxygen first and then second step condense, resonate, whatever, we're okay. And we end up with our amide. All right, and then we can go ahead and, I'm sorry, this is technically NH minus. It's got to grab another proton. And then we can go ahead and hydrolyze this as before if we needed to. All right. There we go. And so if we then throw this with acid and heat, we'll go ahead and get it all the way back to our carboxylic acid, if we throw acid at this. All right, so there we have it. Fun stuff. All right, so scroll just a little bit. First step, nucleophilic attack by hydroxide. We end up with our negatively charged imide, attacks a proton, forming more hydroxide. More hydroxide comes, plucks off a proton from the OH, causes that to close down to a carbonyl, which then puts another lone pair on our nitrogen, which is going to then take another proton away from another water. So we use two OHs, we get two OHs out, so it is still a catalyzed reaction, and we end up getting our product, our amide, which then we can hydrolyze if we were so inclined. Alrighty. So let's look at a couple other reactions here. Let's take a look at what happens with nitriles. And yeah, go ahead. Like over here. Oh, so the hydronium is there too. It's so technically, remember when you, if you're still, you can do a base hydrolysis of this, you end up with this thing, technically. The H3O plus is just to protonate it at the end. So if you keep cooking this thing, you can get it to form the carboxylate. But in order to get the carboxylic acid, you need to do an acid wash. So otherwise, we'll end up with the carboxylate, if that makes sense. So if you used NaOH, you're going to have the sodium carboxylate of whatever your acid is going to be. But if you want to isolate the acids specifically, you need the H3O+. Cool. All right. So great. Let's take a look at a few more reactions. And then we'll do some examples of some of these things. So nitriles with Grignards. Pretty straightforward. Remember that Grignard reagents are carbon nucleophiles. All you get here is this imide ion. And if you treat this with acid, you'll end up getting a ketone out. So technically, first step, you'd protonate, make the imine. And as we remember, imines and ketones can be, they're kind of interchangeable in the presence of water, right? If we put an imine with water, we'll get our ketone or aldehyde out. So don't forget that stuff. That's kind of what's happening here. So we make the imine. This is the imide, or imide, I guess. And then we get the ketone out afterwards from there. All right, so we can put a carbon onto a nitrile, and we'll end up with a ketone. So it's an interesting thing. So the reaction stops at this imide, and so you don't have multiple Grignards attacking. Like if you had a carboxylic acid or an ester or whatever, well, the acid, never mind. If you had the ester or an acid chloride or an anhydride, you attack twice, right? And you end up putting two units of your Grignard on. With nitriles, you only put one. So it's as if you used a Gilman reagent with an ester or one of the other derivatives. Because remember, Gilman reagents only give us the ketone as well. So we're going to see that the same thing will happen here. All right, so we end up getting the imine back, and then we hydrolyze to the ketone. We can also do some reductions. This is one we've seen before. If you do your lithium aluminum hydride, you're going to want excess of this, by the way, or at least two equivalents. You'll end up with your primary amine. This is one we saw as one way to make primary amines, right? We saw we had the Gabriel synthesis, we had the reduction of a nitrile, and then we had the reductive amination, right? So we had three different ways to make amines that we saw, although there are more, but those are some examples, right? This is one that we did see. So remember, you can go start at a nitrile, and you can end up at a primary amine by reduction. So one way to do that. We can also see that if we wanted the aldehyde instead, if you use the diisobutyl aluminum hydride, you can get the aldehyde out. Remember that dibar? Now I should really be consistent with my capitals. Is diisobutyl aluminum hydride. So here's our aluminum. Isobutyls on it. So it's a reducing agent, but it's not as good as a reducing agent as lithium aluminum hydride is. So it stops at the aldehyde. Technically, you first make the imine, and then you hydrolyze to the aldehyde. So you should note that. So the first step, you technically make your imine. You're putting one hydrogen on it. So you're putting the hydrogen attacks the carbon, pops open the C triple bond N, makes something very much like this, the imide ion, except our R prime is an H, and then we will need to hydrolyze that to the aldehyde. Since this time, like last time we used a Grignard, it added a carbon component. Using the dibar, it adds one hydride, so instead of a ketone, we end up with an aldehyde as a result. So, wow. Look at all the stuff we've done. uh, how many reactions was this that we covered? Like 50, it feels like. Let's do some problems on how we might do some of these transformations. Go ahead. Yeah, so the diabot and water. So technically the diabot makes the imine and then the water makes the aldehyde. So it's very important that you include the water in that step. So yeah. It's here, I'll make that more clear. There we go. So the diabot itself makes the imine or imide, the negative charged version, and then the water will hydrolyze it to the aldehyde. All right, so we have 800 reactions we've covered. Let's what shall we do? Let's see. Let's do some stuff. Let's do some practice. How might we get this thing to happen? How might we get this? Actually, no. One too many carbons. There we go. How might we get this? Let's take several ways to do this. What's different? Hopefully we can see that pretty easily. Yes, right. We've changed from a carboxylic acid to an amide. That's all we've done with this molecule. How might we do that? A couple of ways here. One way a little bit easier than the other, but how might we get this done? This will be multiple steps. So this is not just one. Yes, of course. Very good. Yes, you will need multiple reactions to get this to happen. I like it. How do we do it? Okay. Now what? I like it. Which gives us what? What does this give us? Yes, the amide. And then? Hydrolyze it would get us back there. Anti-hydroxylation. We're getting rid of hydroxides. How do we get rid of that double bond O? Don't say Clemenson. Clemenson works on aldehydes and ketones, not on amides. Two ways to do this technically. Yeah, that'd be the way to do it. Technically, you'd want excess of that. Technically, if you can also make this into the nitrile. and then you can use LiAlH4. It's an extra step to do the same thing, right? So either way would work. So the nitrile is just a little bit more reactive, so can make it happen a little bit more quickly, but either way will work, right? So it's an extra step, but it may be worth it for the efficiency of the reaction. So yes, but just going from the amide directly, yeah, go ahead and throw some reducing agent at it, and poof, you're done. Mm-hmm. 2+, I think, is what we put. Maybe. So you need at least 2 equivalents of it. So usually we just, being lazy, just writing excess instead of 2+. So like it might be like 2.2 equivalents. Like a slight excess is fine, but you need at least 2 equivalents. And of course, the more you have, the more likely the reaction is to happen, right? So that'll help that out. All right. Questions on that one? Probably not. Especially not with the with this amide. With the nitrile, maybe you can get away with that. Nitriles are a bit more reactive. You may be able to use sodium borohydride, but not with the amide itself. The amide will definitely not react with NaBH4. Leave that up here. Let's do another one. Oh, let me just think for a sec here. Okay. There we go. Yeah. Bit tougher, this next one. Bit tougher. So with this one, obviously the difference is we have a ketone now, where we had nothing, and we have also got 2 more carbons. Right, so using reactions from this kind of more recent stuff we've done, don't just say, I'm going to turn this into a Grignard reagent and react it with acetyl chloride or something. That's not going to work right anyway, because you'd end up getting an alcohol instead. But let's try to use reactions from the more recent chapters. So how are we going to make a ketone from what we've learned this chapter? Couple of ways. We covered one today. We covered one last time. What are those 2 ways? Yeah, nitrile with Grignard. That's one way to make a ketone. Or what's another way? From last time, remember we have the yeah, it's the Gilman. I'm just trying to think acid derivative. I'm just gonna say plus Gilman. So that can either be an acid chloride, anhydride, or ester. So one of those things, and a Gilman reagent. That will get us to where we need to be. But let's consider. We know how to make an acid out of this toluene molecule, right? Throw some KMNO4 on it. Now it's a carboxylic acid. But we also have our ketone is not on the same carbon there. But we do know that nitriles add an extra carbon, right? Nitriles always add an extra carbon to your molecule. So that might be the better way to go. That might be the better way, because if we tried to use an acid derivative of a Gilman, if this thing were the acid, and we used a Gilman reagent on it, if we use ethyl diethyl lithium cuprate, we'll get this. We have the ketone on the wrong side, right? And yes, you can find whatever, you can dehydrate stuff and do your oxidative cleavage and have fun and blah, blah, blah. But using just what we've done this chapter, nitrile and Grignard is going to be the way to go. So what might that look like? What Grignard and what nitrile would we use for this to get that ketone out? From what now? Yeah, we're working in reverse. Because this one's a little bit harder. So what's the nitrile that we need here? I'll tell you right now, our Grignard, we're adding just the methyl group, right? Because the nitrile will add 1 carbon to our original molecule. Our final molecule has 2 carbons extra. So if the nitrile adds 1, we only need to add 1 other carbon with our Grignard, right? So indeed. So what's the CN compound going to look like? Well, let's look at. Well, of course, but where is that nitrile going to be? That's what I'm looking for. Or here, let's do it. Let's do it this way. Which of these carbons that I've numbered, 1, 2, or 3, is going to be the C triple bond N? All right. So if we have that, it's number 2. Yeah. If we had that and we put the methyl Grignard on, we're going to end up with, again, this thing. So yeah, we need this to be our nitrile. And let me fix the geometry on that. So we need this nitrile, right? Because that would be the purple carbons 1 and 2, and right, this methyl thing will be carbon. I'm sorry, that'll be carbon 1. I'm sorry, I forgot how I wrote them. Oh my gosh. So just keeping track of all of our carbons, right? So the methyl group from our Grignard is going to be carbon 1. Carbon 3 is still there. Carbon 2 is the one that our nitrile is going to be on. So remember, the reagents will also need water on this. So we'll need our methyl MIGBR and then the water. Cool. So how are we going to go from toluene to this nitrile? Benzyl nitrile. Yes, yes, yes. So I like that. Let's use a bromine. Okay. What are the reagents necessary to get from this brominated species to the nitrile? No. No. I mean, BR2 kind of, yeah, that would work, but there's a special reagent that will. Well, first off, you're giving me reagents for this step. I want reagents for bromine to nitrile. Give me that one. And then we'll talk about the BR2 in light. Or, yeah. So KCN and like acetone or something, right? You'd need some SN2 type process. So cool. All right, so putting the bromine on though, yes, Br2 would work. Br2 and light would work, but we have something better for this. How do we brominate the benzylic positions selectively? It's from, I would say, the aromatic chapter. It's also from 105. It's something we've used a lot. Like, it's NBS, right? NBS is our savior here. NBS will brominate this position. Um, so that's the winner here. So NBS will brominate the benzylic position. Awesome. Now we can go ahead and substitute that within nitrile. Notice we've added one more carbon by doing that. This step adds one carbon, and this step also adds one carbon. So great. And then we can go ahead and just use our water, and we'll end up with the ketone there. Fun. So notice we had two extra carbons in our molecule. So we had two reactions that each added one carbon to our molecule, and so we ended up with our product. Now, this is probably the most efficient way, I would say, to do this. It's only 3 steps. Pretty good stuff to add 2 more carbons. Alrighty, well, let's go ahead and look at some more things. Any questions on this one that we'd like to, or any of the steps we want to look at more closely or anything? Or all right, let's do some predict the products then. All right, here we go. Actually, we don't need access there. And then let's do. All right, here we go. Cool. So we've got 4 steps here. What sort of fun stuff might we employ? Or rather, what's going to happen? To where? I know what you're saying. Ta-da! Yes, that is step 1. What does step 2 do? So we're just predicting the products, but I'm going to just show you the work, like stepwise, what's happening. So like, yes. So step 2 would replace that with a double bond O, so we make the ketone instead. Great. Third step. What? How? This is alcohol. A primary amide would be something like that. So I'm like, how are you putting an N in there? Oh no. Oh no. Oh yes, yes. That will give you a primary amine, not an amide. Yeah, just making clear there. So okay, so LAH4 technically will make this O minus, and then of course the water will make it to the alcohol. So that's the 4 steps that are happening here. Because why not? We should always have some fun stereochemistry. So, racemic mixture. Cool. All right, let's see. What if I wanted to make... Let me find some examples here. These are so easy, though. Like, yeah, why not? We'll do it. Okay. Here we go. Apparently, we're using cyclic things all the time. BR. Nope. Should still be 5. All right, how might we make this thing? So let's analyze what's different about the structure. Of course, we have the bromine gone. We've added more stuff. We did make an ester, so that's the functional group we have, right? What else is like added on to our structure? So the ester would be this part, kind of. But we've added one more thing also. We also have, so the ester, like, remember how to make esters, right? We were going to throw an alcohol in with some sort of acid derivative, right? That alcohol will carry these 2 carbons. So if we use either an acid halide or an anhydride or an acid or whatever, we would put ethanol. Ethanol would give us that part of the ester, right? That would give us that half. So we see here that we still have 1 more carbon to put on that we didn't have in the original molecule. So the ethanol, those 2 carbons come from ethanol, right? Or technically, I mean, we could do some really crazy stuff, but yeah. And the oxygens, we can come up with elsewise. But it's also very important that we just take a look at the number of carbons that are changing, because those are the more like significant changes. Otherwise, yeah, just changing functional groups. Now we've added carbons on. So 2 of those carbons come from ethanol. We have 1 more carbon that we need to account for. And so how might we get that carbon to be there? Yeah, that'd be a great idea. Anytime you have 1 carbon, nitriles are a great way to go. All right, so we're starting at the beginning then. All right, we can do that. We've added 1 more carbon to our molecule. Hooray. All right, so now what? And I guess if we're going to be good, we should have a solvent. How about we use DMF this time? Yes, that could work. What grignard do you want to use? Yes? This is an interesting thought. I hadn't thought to use a Grignard, but go ahead. Yeah, what Grignard would we get? So Grignard would get us a ketone, right? We do know how to make ketones into esters, but unfortunately we're going to make the wrong ester. So I wanted you to fail. I wanted us to see that. If we tried to use something like ethyl Migbur, we would end up with this. And if we say, let's do a Baeyer-Villiger oxidation to get the ester, that would actually put it on the other side. So that. Okay, so Grignard's out. Interesting thought, though I don't know if you had thought that far ahead, but unfortunately, well, actually, no. If we use like a, no, let's not even think about the Grignard anymore. So not going to work. All right, what else can we do? Sure, that works. Okay. All right. Okay, what do you want to do now? What? You could do that. That's the thing. There's plenty of options that work. Right? What are we going to do for the next things? All right, let's go from the aldehyde to the ester. How are we going to do that? By the way, this was H3O plus heat. What are we going to do now that we have the aldehyde? How are we going to get the ester? Okay, that would work. Well, now you can use Fischer. Well, now you can. Yeah, we have the same thing. Oops. Yeah, that works. Aldehyde, though, extra step. So it is just more efficient to go directly to the carboxylic acid rather than go to the aldehyde and then oxidize it. So I would say it'd be better to take the bottom route here, make your nitrile, then hydrolyze it to the acid, and then go ahead and do your Fischer. Or if you want it instead, that would be one way to do it. Alternatively, you can use thionyl chloride, make it into an acid chloride, and then use ethanol. Probably a little more efficient, with pyridine, of course. Because the Fischer esterification, as you know, it's reversible. But if you use the thionyl chloride and then the ethanol pyridine, you'll get your ester out kind of more efficiently, if that makes sense. So for Fischer versus the thionyl chloride, and maybe not, but for the aldehyde way, I probably would. Because that's just an extra step that we're using a reagent to specifically get an aldehyde, and then we're going to oxidize it anyway, so it's kind of like, it's two steps to do the same thing. right? That's the efficiency I'm worried about. Like 2 transformations. So you have to use the diabond, get your aldehyde, isolate that, do all the workup, extract it, then you oxidize it. So you're adding a whole nother step. Like, I don't mean step as in like this is 2 steps, because it's just really you add 2 things in a separate order, right? Like that's not 2 steps. I wouldn't consider that 2 steps. But this would be 2 steps where we make the aldehyde and then the carboxylic acid. That's 2 steps. Same thing with like the thionyl chloride and the ethanol. Like you don't really need to work it up in between, so you can go ahead and just throw them in afterwards. So that's kind of more what I'm going for. So if there's a much easier way to get to your thing, like if you I don't know, if you like decided to put a Grignard on this thing, put a methyl group, attack the brominated, or I don't even know what you do. If you were to make an alkene and then cleave it to make an alcohol and then oxidize the alcohol, like we might have some problems because there are easier ways to do these things. So, like, I'm in terms of efficiency, if it's a reaction that we've covered that is fewer steps, I would suggest that that would be the best way to go. Will I take points off? Maybe. How many? Probably not too many. Because if you're making the product of interest, that's the main point, right? So you'll get most of the credit for that. Okay? Yeah. No, okay, that would be this this step right here. Instead of doing a Fischer esterification, it would be that step. So yeah, I realize that's totally off to the side. So so yeah. All right, but yeah, again, Fischer esterification versus make the acid chloride and then do it. Like, we're okay. All right, shall we do another one? Oh, this is an interesting one. No. Well, here, I'll do a Chamras. Why don't you do this yourself? Okay. Yes, of course. Uh, actually, I think this needs to be. There we go. Let's go ahead and I'll give this to you. 1, 2, 3, 4, 5, 6, 7. Okay, have fun. Do this. We'll start here next time. Well, actually, I mean, we're all the stuff that we've covered today. This is where it ends for our exam. So next time we'll finish this problem, I guess. You'll do more in lab, hopefully, unless he cancels, and then we'll start enolates. Enolates will not be on your exam 3. So, but we will keep moving forward. Okay? Cool. Awesome. So see you guys on Monday. Enjoy your weekends. And I'll see you then. All right? Awesome. Okay. Of course. All right. Take care.